So at one point or another we have to settle this. What the hell is the big deal with factoring polynomials? We've been factoring forever. Why? So it turns out that solving equations in any algebra class is a huge deal. You've got to be good at solving equations. These are riddles about numbers. I've got a number, I don't know what it is, but if I multiply by 3 and I get 12 or something like that. That's a big deal in algebra, in any algebra class, in mathematics in general. You want to know how far should you shoot the rocket so you get to the moon, or you want to know how fast should you make the artificial heart pump to get X amount of oxygen into the lungs, or whatever. These are huge, huge questions. And so solving equations is a big deal. As it turns out, the key to solving these harder equations is in fact factoring. Factoring is so huge. It is exactly the key to solving harder math equations. So that's why we're spending so much time on factoring. Factor by distributive law, factor by grouping, factor by splitting the middle term, blah blah blah. So let me try to explain this connection between factoring and solving hard equations. Okay, so I'm going to try to explain it here. Here's a problem that we did earlier. In fact, we did it over here. We got that that's equal to x plus -1 and x plus 5. X plus -1 and x plus 5. Okay, that's factoring. Now consider a different world over here where you have to solve equations, and this equation may be a little harder than the ones we're used to because we're only used to degree 1 equations, but the equation may go something like this. I've got a number in my pocket. I won't tell you what it is, but I'll give you a hint about it. If I square the number and I add 4 times the number and then I subtract 5, I get 0. Can you guess what the number is? Yeah, this could make you the life of the party if you can do stuff like this. And so this may not be such an easy equation, but it turns out that this is exactly the key. And let me explain the connection. The connection goes something like this. There is something famous in another little famous theorem that we haven't talked about. It's called the zero factor theorem. Zero factor theorem. Okay, and it goes like this. If I've got two numbers in my pocket, a times b, and when I multiply them, if I get 0, you're going to think, no way, there's no way that you can multiply two numbers and you get 0. And you start to think about it for a little bit and you say, well, maybe if one of them was equal to 0, maybe that could have happened. A is equal to 0 or b is equal to 0. Not only that, but that might be the only way that this can happen. And that's powerful, that's amazing. That's called the zero factor theorem. Very simply it says, if you got two numbers in your pocket and when you multiply them you get 0, it's only one way that can happen. You had to have had one of them being 0 to begin with, at least one of them. Okay, if they were both neither 0, then the product would have not been 0. Steep. It doesn't work for other numbers. Look, if I have a number times another number and they're equal to 12, you can't say, well, one of them is 12. No, they could be 3 times 4, and that gives me 12. Or maybe it could be 2 times 6, and that gives me 12. Or it could be 5 times 12 over 5, and that gives me 12. You see how crazy other numbers are? But 0 is special. It does this really better than any other number. If you multiply a number times another and you get 0, then one or the other one must be 0. What that means is that anytime you have, if I have triangle times square and that's equal to 0, well then triangle is equal to 0 or square is equal to 0. That's what it means. That's a zero factor theorem. And that right there that provides the connection to these two ideas. Because watch this. I have this crazy problem, degree 2 problem. This tells me the degree 2. And here's the proposition. I have something plus something plus something is equal to 0. I'm going to turn that into something times something using the work I've done before. X plus -1 times x plus 5 is equal to 0. Okay? See the work that we did before. And now look what we've done. Now, instead of having something plus something is equal to 0, now I have something times something is equal to 0. Whoa, that changes everything. Every time I have something times something is equal to 0, zero factor theorem time. Wait. Zero factor theorem time. That means that either x plus -1 is equal to 0 or x plus 5 must be equal to 0. That's a zero factor theorem. We'll talk more about this next section. I'm just giving you a little taste so you can see the exciting connection between factoring and solving. See, that's amazing. You take your big degree 2 monster problem And the zero factor theorem allows you to write into two super simple innocent problems. This is a degree 1 problem. See, x plus negative 1 is equal to 0. This is a baby problem for infants. This is a super easy problem, x plus 5 equals 0. You're taking your super difficult problem here, a number in my pocket, square it, add 4 times the number, subtract 5, you get 0. Huh? I know. And now you factored it, and now this turns it into duck soup. Something times something equals 0. Well, that can only happen if either the first something was equal to 0 or the second something was equal to 0, leading you to the conclusion that x must be equal to 1 or x equals to negative 5. Here I added 1 to both sides. I added 1 to both sides. Boom. I added negative 5 to both sides. Boom. See why they pay me? That's it. You solve the riddle. And that provides the connection between factoring and solving. If you can factor, you can solve amazingly difficult questions, so long as you're excellent at factoring. And that's why we're spending so much effort in factoring polynomials. Alright, that gives you a big picture view of things. We should do one more factoring technique, and that's called recognizing famous polynomials. So it's called factor by recognizing your famous polynomials. Alright, let's take a little cut here and we'll come back and do that.